Hello everyone, I'm Mayur and the topic discussed in this video is strain sensors using carbon nanotubes for human motion detection. The outline for this video is as follows. First, we'll start with a slight introduction to the topic, then we'll try to understand what are strain sensors in general, and further, what are flexible or skin mountable strain sensors, and finally, the three fabrication methods that I've reviewed along with the results in conclusion. So, first off, why is there a need for nanotechnology in fabricating sensors that are wearable or skin like, and what are its applications, and why do we need such sensors? So, understanding the skin's material properties and natural motion is critical for applications ranging from tissue engineering to spacesuits. While there is an extensive understanding of human skin properties based on active tensile testing, there is a little knowledge of the strains experienced by skin during natural movements. These skin-like strain sensors are essential components of electronics and optoelectronic devices that facilitate human interaction and biofeedback. Some important attributes or features of these sensors, they are super flexible, stretchable, ultra soft, they have reverse stretchability, can sense pressure, are physically and mentally robust, have high sensitivity, are easy to fabricate, and many more. Also, there is a significant rise in demand for such sensors because of its growing applications and uses. Use of nanotechnology has made it quite possible for these sensors to have high resistance, miniaturized active area, and makes integration easier because of its small size. The technical definition states that strain sensors transduce mechanical deformation to electrical signals such as change of capacitance or resistance. It is one of the most important sensor for electronic measurement of mechanical quantities. Also, it is able to pick up expansions and contractions of the structure. They exhibit excellent hysteresis performance at different strain levels and rates with high linearity and small drift, and they are also known as strain gauges. They are commercially available, and some strain sensors are based on metal foils and semiconductors that are available in the market, and they also have low cost of fabrication. But in general or standard sensors, as that one shown in this picture, um, they have certain limitations such as poor stretchability, have fixed size, and are non-wearable or not skin mountable. So, what are flexible and skin mountable strain sensors? So, there is a growing demand for flexible and soft electronic devices in particular. In particular, stretchable, skin mountable, and wearable strain sensors are needed for several potential applications, including personalized health monitoring, human motion detection, human machine interfaces, soft robotics, so on and so forth. Also, such sensors are being developed by new mechanisms such as disconnection between overlapped nanomaterials, propagation in thin films, and tunneling effect that are different from traditional strain sensing mechanisms. The three fabrication methods that I've reviewed or discussed in this video are carbon nanotube silicon rubber based strain sensors, graphene woven fabrics on polymer and medical tape composite film, and spray deposited films of single walled carbon nanotubes. First one is using carbon nanotubes and silicon rubber. Carbon nanotubes have excellent mechanical, electrical, and thermal properties and are used in flexible electronic devices, sensors, actuators, and biomaterials. They are more efficient in comparison to conventional strain gauges that we have discussed earlier. Carbon nanotubes, in combination with PDMS, also known as polydimethylsiloxane, have shown poor sensing performance. The proposed solution in this method is the use of EcoFlex as a substrate. The sensor made from this process consists of CNT EcoFlex nanocomposite thin films laminated between the top and bottom layers of EcoFlex. The nanotubes used are multi-volt carbon nanotube tubes with a length of 5 to 20 micrometers and diameter of 16 nanometer. 0.05% weight of non-functionalized carbon nanotubes in isopropyl alcohol are sonicated for an hour. This results in formation of agglomerated carbon nanotubes in isopropyl alcohol medium. When stretched, the reorientation and repositioning of carbon nanotubes increase the base resistance of sensor. When relaxed, this elastic force of EcoFlex recovers the resistance. Mm, the liquid polymer is allowed inside the porous carbon nanotube network thin film in a controlled manner. Air spray coating is used for deposition of carbon nanotube thin films. The resistance and thickness of CNT films can be controlled by the density of sprayed solution. The CNT solution is patterned at 100 degrees Celsius to obtain percolated thin films. The liquid Ecoflex is cast on CNT film and cured at 70 degrees Celsius. Copper wires are connected to two ends of the CNT film using silver paste. The experiments were conducted by mounting sensors on different body parts. The images show the different results when sensor was applied on finger, wrist, and elbow. Next step is graphene woven fabrics on a polymer and medical tape composite film. Graphene has some cool properties like ultra translucency, high mechanical flexibility and stability, high restorability, and high carrier mobility. It is a simple structured, low cost graphene woven fabric strain sensor. The high density cracks in network leads to decrease in current and increase in resistance. Due to its crisscross configuration, GWF exhibits extremely high gauge factor. To make it wearable, adhesive medical tape with PDMS glue was used. The process starts with CVD by graphene growth on copper mesh. Etching of copper is done in FeCl3 or HCl solution. The GFWs are then transferred to a pre-treated film composite with medical tape and PDMS. This arrangement is connected to silver wires with silver paste on both ends to obtain the final product. The sheet resistance of GFW was recorded at about 400 to 500 ohms per square meter. The results show strain graphs of hand movement and movement of hand muscles, also the effect of eye blinking on cheek and its surrounding area. Lastly, we have spray deposited films of single walled carbon nanotubes. It consists of transparent and spray deposited single walled CNT films. These spring-like structures can accommodate strains up to 150%. They have conductivity as high as 2000 Siemens per centimeter. There are different steps involved in fabrication. The first one is preparation of substrates. PDMS is poured against polished silicon wafer. The wafers are activated with oxygen plasma and passivated by vapors of 1-trichlorosaline. This arrangement is cured in oven for 2 hours at 60 degrees Celsius. Second step is preparation of carbon nanotube solution. The arc discharged SWNT are ultrasonicated in N-methylpyrrolidone for 30 minutes. This solution is centrifuged at 8000 rpm to remove carbon and other contaminants. Next step is spray coatings and dependence of contact angle on strain. CNTs are coated using airbrush. The substrates are activated using ultraviolet light. Fabrication of capacitive arrays. The PDMS substrates are stretched to 25% before laminating them. Ecoflex was mixed, degassed, and spread over substrates to produce the pressure sensors. And the resistance versus strain graphs were measured using different programmable stages. From the results, we can see that the first figure shows the change in resistance versus strain for film. When the film is strained, resistance increases and remains constant as strain is released. When strain is increased again, resistance remains constant and then increases when permittivity exceeds the value at which the strain was released before. Figure B shows resistance versus time in response to 4 cycles of stretching from 0 to 50%, and figure C shows resistance versus number of stretches over 12,000 cycles of stretching at 25%. So these are the references that I've used for this topic, and thank you very much for your time.